Friends, we'll solve now 10 questions on number system. This is Atanu Chaudhary. The first question. If 3 to the power 4x times 9 to the power 6x equals 81 to the power 8, find the value of x. Let's show you the three basic principles we'll use to solve this problem on indices. The first indices principle states, if a to the power x equals a to the power y, as bases on both sides of the equation are equal, the powers also must be equal, that is, x equal to y. The second indices principle states, when a to the power x is multiplied with a to the power y, the result is a to the power x plus y. Bases being equal, the powers are summed up. And the third indices principle states, if a to the power x is again raised to the power y, the result is a to the power xy. The powers are multiplied together this time. But to apply these principles for solving our problem, the bases of all the three terms of the equation must be equalized first. This is what we call base equalization technique. Question is, what should be the equal base value of the three terms? As 9 to the power 6x and 81 to the power 8 are both in powers of 3, the target base value must be 3. Now bases are equalized to value 3. This is the time to use the third indices rule to combine the powers of the two terms to 12x and 32. To combine the two LHS terms to a single term now, apply the second indices product rule on this result. Finally, as bases on both sides of the equation are equal, powers are equal. Here the first indices rule is applied. So, powers being equal, 16x equal to 32, that is x equal to 2. Answer is option A, 2. Second question. Which one of the four numbers 81, 125, 343 and 64 is a perfect square as well as a cube? To be a perfect square and also a cube, the power should be a product of 2 and 3, that is 6. Express the four choice values in power of prime integers. So with power as 6, 2 to the power 6 equal to 64 is your answer. Answer, option D, 64. Third question. When the unequal digits of a two-digit number are interchanged in position, the absolute value of the difference of the two numbers would always be divisible by which one among 5, 7, 9 or 11? Apply place value mechanism to express original number nxy as 10x plus y, where x is tens digit and y is units digit. On interchange of the digits, the new number form becomes nyx equal to 10y plus x. Absolute value of the difference of the two is nxy minus nyx equal to 9 times x minus y. As x is not equal to y, x minus y is not equal to 0. So, absolute value of the difference will always be divisible by 9. Answer is option C, 9. Fourth question now. If two bells chime at intervals of 4 minutes and 15 minutes, after how long would they chime together first if they had chimed together in the beginning? This is a question on LCM. The two bells will chime together only when a multiple of 4 minutes becomes equal to a second multiple of 15 minutes. In other words, it will be the elapsed time after the start, which is the lowest common multiple or LCM of 4 minutes and 15 minutes. In fact, the two bells will continue to chime together at every such elapsed time. There is a multiple of LCM of 4 minutes and 15 minutes. Think over. The synchronization graphic will help you to visualize the situation. As explained, 15 numbers of 4-minute intervals coincides first time after the start with 4 numbers of 15-minute intervals. This time duration of 60 minutes is the LCM of 4 and 15 and is the first time after start when the two bells will chime together again. LCM of 4 and 15 is 60, as 4 and 15 have no common factors. So it will take exactly 1 hour from the beginning for the two bells to chime together again. Answer option D, 1 hour. Fifth question. How many numbers from 20 to 50 have no number from 2 to 10 as factors? The single digit numbers 2, 3, 5 and 7 are the only 4 prime factors in the set of numbers from 2 to 10. The smallest non-prime number having none of these 4 factors is 11 square, that is 121. So we have to find only the prime numbers in the range from 20 to 50. Think it over. You can easily enumerate these prime numbers as 23, 29, 31, 37, 41, 43 and 47. A total of 7 numbers. Answer option C, 7. Sixth question now. 256 times 256 minus 144 times 144 divided by 112 equals how much? Seems that evaluation needs a lot of calculation. But the pattern that avoids almost all the calculations is the numerator is in the form of a square minus b square equal to a plus b multiplied by a minus b, where a equal to 256 and b equal to 144. With a equal to 256 and b equal to 144, a plus b is conveniently 400. And still more conveniently, a minus b is 112. This would cancel out the denominator. So final result is just 400. Answer option B, 400. Seventh question. The number formed by interchanging the tens and units digit of a 3-digit number is more than the original number by 63. What are all possible values of the units digit of the original number? To solve the problem, we'll use the place value mechanism in this case. Let's assume x, y and z to be the hundreds, tens and units digit of the original number. The original number can be expressed then as 100x plus 10y plus z, and the new number after digit interchange 100x plus 10z plus y. Difference between the two is 9 times z minus y. And as given in the problem, this difference equals 63. Simplify to get the result z equal to y plus 7. This means value of z starts from 7 with y equal to 0 and can only be 8 or 9 in addition. So all possible values of units digit of the original number z are 7, 8 and 9. Answer option A, 7, 8, 9. Eighth question. Find the sum of all the 3-digit numbers, each of which on division by 5 leaves a remainder 3. First we will find how many such 3-digit numbers are there. To count the numbers systematically, divide the whole 3-digit number range of 100 to 999 in 9 smaller ranges. 100 to 199, 200 to 299, 300 to 399 and on to 900 to 999. Target numbers in the range of 100 to 199 are 103, 108, 113 on to 198. A total of 20 such numbers. Verify if you need. In each of the 9 such ranges ending at 999, behavior will be same and such numbers will count to 20. So such numbers in total are 9 times 20 equal to 180. Sum of these 180 numbers in arithmetic progression is s equal to 103 plus 108 plus 113 plus plus 988 plus 993 plus 998. A total of 180 terms with first and the last term as 103 and 998. Sum of an arithmetic progression is given by the sum of first and last term multiplied by half of the number of terms. The sum in this case evaluates to 90 times 103 plus 998. This equals 99090, but by number estimate you can identify option D 99090 as the answer without evaluating the product. You can also solve this problem quickly even if you don't know what is arithmetic progression, let alone its formula. Look at the sum of 180 numbers, 103 plus 108 plus 113 ... plus 998. Final result will be 180 times average of these 180 numbers. You can conclude with certainty from the series that average of the sum must be much greater than 103. Now mentally divide the choice values by 18 after stripping the rightmost digit of the choice values. First choice value 180 is too low. For second choice value 1550, quotient is 8. And for the third choice value of 6995, quotient is less than 40. Both quotients being less than 103, the fourth choice 99090 must be the answer. Answer option D, 99090. Ninth question. Find the units digit of 264 to the power 102 plus 264 to the power 103. At first glance, it seems the solution would be laborious and time-taking. But the key pattern that 264 to the power of 102 can be taken out of both the terms as a factor greatly simplifies the problem. Result is 264 to the power of 102 multiplied by 265. Now 264 raised to any positive integer power will always remain even. Think over. So units digit of its product with 265 will be 0. As 5 of 265 multiplied with an even number will always produce a units digit 0. Answer is option A, 0. Last question. Find the units digit of the number 2137 to the power of 754. Let's state the first principle of units digit of a number, say ABCDU raised to the power of, say, n, as units digit of u to the power n. This is because when the original number is multiplied with itself n times, its units digit is multiplied only with itself also n times without any carryover into it. So units digit of 2137 to the power 754 is equal to units digit of 7 to the power 754. Let's now explain the second principle of units digit of a single digit number raised to the positive integer power of n. When a single digit number, not 0 or 1, is raised to any positive integer power, the units digit of the result takes one of the few fixed values specific to the single digit number. We say the units digit cycles through these few fixed values. To make the concept clear, let's show you the result of raising 7 to the power of 1, 2, 3, 4 and 5. The units digit becomes respectively 7, 9, 3, 1 and then 7 again. The cycle of length 4 is completed at 1. The fixed set of values are 7, 9, 3 and 1. To use this concept in finding the units digit of 7 to the power 754, you have to divide the power 754 by the cycle length of 4. Remainder will be 2. The rules for final units digit are: for remainder 1, units digit is 7, the first digit in the cycle. For remainder 2, units digit is 9, the second digit in the cycle. For remainder 3, the units digit will be 3, the third digit in the cycle, and for the remainder 0, the units digit will be 1, the fourth and last digit in the cycle. Think it over. In our case, as remainder is 2, the units digit will be 9, the second digit in the cycle of 7931. Answer is option D, 9. This is where we end the solutions of the 10 questions. For going through the detailed solutions, please refer to the article in our website suresolve.com. The link is in the description of this video. And before signing off, we should remind you, please subscribe to our channel if you find this video useful. Happy learning!